Hello students, welcome to the lecture on simulation, and after this lecture we will be able to learn the following objectives. Give details of the development of simulation model. Talk about the advantages and disadvantages of simulation. Give details of the Monte Carlo simulation. Talk about the simulation of demand forecasting problem. Explain the simulation of queuing problems. Give details of the simulation of inventory systems. A simulation of a system is the operation of a model of the system. The model can be reconfigured and experimented with. Usually this is impossible, too expensive or impractical to do in the system it represents. The operation of the model can be studied, and hence properties concerning the behavior of the actual system or its subsystem can be inferred. In its broadest sense, simulation is a tool to evaluate the performance of a system existing or proposed under different configurations of interest and over long periods of real time. Simulation is used before an existing system is altered or a new system built to reduce the chances of failure, to meet specifications, to eliminate unforeseen bottlenecks, to prevent under or overutilization of resources, and to optimize system performance. For instance, simulation can be used to answer questions like, what is the best design for a new telecommunications network? What are the associated resource requirements? How will a telecommunication network perform when the traffic load increases by 50%? How will a new routing algorithm affect its performance? Which network protocol optimizes network performance? What will be the impact of a link failure? The system changes instantaneously in response to certain discrete events. The steps involved in developing a simulation model, designing a simulation experiment, and performing simulation analysis are: Step 1. Identify the problem. Step 2. Formulate the problem. Step 3. Collect and process real system data. Step 4. Formulate and develop a model. Step 5. Validate the model. Step 6. Document model for future use. Step 7. Select appropriate experimental design. Step 8. Establish experimental conditions for runs. Step 9. Perform simulations runs. Step 10. Interpret and present results. Step 11. Recommend further course of action. Development of simulation model. Simulation model comprises several steps. Now we will talk about each step in detail. Step 1. Identify the problem. Enumerate problems with an existing system. Produce requirements for a proposed system. Step 2. Formulate the problem. Select the bounds of the system, the problem, or a part thereof to be studied. Define overall objective of the study and a few specific issues to be addressed. Define performance measures, quantitative criteria on the basis of which different system configurations will be compared and ranked. Identify briefly at this stage the configurations of interest and formulate hypotheses about system performance. Decide the time frame of the study, that is, will the model be used for a one-time decision, example capital expenditure, or over a period of time on a regular basis, example air traffic scheduling. Identify the end user of the simulation model, example corporate management versus a production supervisor. Problems must be formulated as precisely as possible. Step 3. Collect and process real system data. Collect data on system specifications, example bandwidth for a communication network, input variables, as well as performance of the existing system. Identify sources of randomness in the system, that is, the stochastic input variables. Select an appropriate input probability distribution for each stochastic input variable and estimate corresponding parameter or parameters. Software packages for distribution fitting and selection include expert fit, best fit, and add-ons in some standard statistical packages. These aids combine goodness of fit tests, example, 2-test, Kolmogorov-Smirnov test, and Anderson-Darling test, and parameter estimation in a user-friendly format. Standard distributions, example, exponential, Poisson, normal, hyperexponential, etc., are easy to model and simulate. Although most simulation software packages include many distributions as a standard feature, issues relating to random number generators and generating random variants from various distributions are pertinent and should be looked into. Empirical distributions are used when standard distributions are not appropriate or do not fit the available system data. Triangular, uniform, or normal distribution is used as a first guess when no data is available. Step 4. Formulate and develop a model. Develop schematics and network diagrams of the system. How do entities flow through the system? Translate these conceptual models to simulation software acceptable form. Verify that the simulation model executes as intended. Verification techniques include traces, varying input parameters over their acceptable range, and checking the output, substituting constants for random variables, and manually checking results and animation. Step 5. Validate the model. Compare the model's performance under known conditions with the performance of the real system. Perform statistical inference tests and get the model examined by system experts. Assess the confidence that the end user places on the model and address problems if any. For major simulation studies, experienced consultants advocate a structured presentation of the model by the simulation analysts before an audience of management and system experts. This not only ensures that the model assumptions are correct, complete and consistent, but also enhances confidence in the model. Step 6. Document model for future use. Document objectives, assumptions, and input variables in detail variables of a simulation model so that we may observe and identify the reasons for changes in the performance measures. The number of experiments in a simulation study is greater than or equal to the number of questions being asked about the model. Example, is there a significant difference between the main delay in communication networks A and B? Which network has the least delay, A, B, or C? How will a new routing algorithm affect the performance of network B? Design of a simulation experiment involves answering the question, what data need to be obtained, in what form, and how much? The following steps illustrate the process of designing a simulation experiment. Step 7. Select appropriate experimental design. Select a performance measure, a few input variables that are likely to influence it, and the levels of each input variable. When the number of possible configurations, product of the number of input variables and the levels of each input variable is large and the simulation model is complex, common second-order design classes including central composite, Box-Behncke, and full factorial should be considered. Document the experimental design. Step 8. Establish experimental conditions for runs. Address the question of obtaining accurate information and the most information from each run. Determine if the system is stationary, performance measure does not change over time, or non-stationary, performance measure changes over time. Generally, in stationary systems, Steady state behavior of the response variable is of interest. Ascertain whether a terminating or a no terminating simulation run is appropriate. Select the run length. Select appropriate starting conditions. Example, empty and idle, 5 customers in queue at time 0. Select the length of the warm-up period if required. Decide the number of independent runs. Each run uses a different random number stream and the same starting conditions by considering output data sample size. Sample size must be large enough, at least 3 to 5 runs for each configuration, to provide the required confidence in the performance measure estimates. Alternately, use common random numbers to compare alternative configuration by using a separate random number stream for each sampling process in a configuration. Identify output data most likely to be correlated. Step 9. Perform simulation runs. Perform runs according to steps 7, 8 above. First, the advantages. Simulations can help in cases where mathematical models are not applicable because the system to be modeled is either too complex, the system's behavior cannot be expressed by mathematical equations, or the system involves uncertainty, that is, stochastic elements. In either of these cases, simulation can be applied as a last resort to gain information about the system. Simulation is especially useful if changes in an existing system are to be made and the effects of the changes should be tested prior to implementation. Trying out the changes in the real system may not be an option because the system does not yet exist. The costs are too high. There are too many scenarios to test. The test would take too much time, weeks, months, years. The changes are not legal, etc. In all these cases, a simulation model allows to test various scenarios in often only a couple of minutes or hours. A disadvantage of simulation in comparison to exact mathematical methods is that simulation cannot naturally be used to find an optimal solution. There are methods which long to optimize the results, but simulation is not inherently an optimization tool. Simulation is often the only means to approach complex systems analysis. Many systems cannot be modeled with mathematical equations. Simulation is then the only way to get information at all. Another disadvantage is that it can be quite expensive to build a simulation model. First, the process that is to be modeled must be well understood, although a simulation can often help to understand a process better. The most expensive part of creating a simulation model is the collection of data to feed the simulation and to determine stochastic distribution. Example, processing times, arrival rates, etc. Another key point is to ensure the model is valid, that is, its behavior mirrors that of the original physical system. For systems that do not exist yet, because simulation is used for planning it, this is especially hard. Insufficient validation and verification of a simulation model is one of the top reasons for failing simulation projects. The consequence is false results, and this lessens the credibility of the method in general. Monte Carlo simulation is a technique used to determine the probabilistic distribution of an outcome that relies on all probable scenarios. Monte Carlo sampling refers to the traditional technique for using random or pseudo-random numbers to sample from a probability distribution. It is a method of recognizing and determining risk. Monte Carlo simulation produces not only one answer, but rather a series of answers or a range over which the results vary as a function of probability of occurrence and also a most expected result. In other words, Monte Carlo simulation generates hundreds of alternatives for a project. The answer may fall anywhere within the range of the results produced. All inputs are independent of one another. Thus, when the variables are correlated, a correction to the Monte Carlo simulation is required. To account for correlation, a correlation matrix in the Monte Carlo simulation is used. The correlation value for each set of variables is entered in the matrix, and when the simulation is run, correlation among the variables is accounted for. Monte Carlo simulation is done using risk analysis software. The results of the analysis may be viewed differently by different people. This variety of opinions is because of the differences in the level of acceptable risk among individuals. Simulation of demand forecasting problem. These analytical requirements necessitated an extremely detailed approach to demand forecasting. Rather than identifying trends in aggregate or sector electricity consumption and their determinants, the Council developed a forecasting system that builds demand forecasts up from the end-use details of each consuming sector: residential, commercial, industrial. For example, the commercial sector demand forecasting model contains the structure for estimating electricity demand for 9 types of buildings, 8 specific end users, and 3 fuel types, new and existing buildings, and for customers of publicly owned utilities and investor-owned utilities separately. This means that there are 960 components to the commercial sector demand forecast. Similarly, the residential sector model identifies 3 house types, 4 fuels, 8 end users, utility ownership, and new and existing homes. The industrial model includes 37 different industrial sectors. Some of the most electricity intensive industrial sectors are modeled by individual plants and by end users of electricity. The less energy intensive industrial sectors are based on economic relationships among fuel and electricity use and measures of sectoral output and energy prices. Forecasting with these models requires detailed economic forecasts for all of the sectors that are represented separately in the demand models. The models also require forecasts of demographic trends and fuel prices. In addition to the sectoral demand models, the demand forecasting system contains an electricity pricing model. The pricing model adds new generating resources as needed to meet electricity demand and adds up the costs of the existing and new generating resources to estimate total electricity supply costs and electricity prices. Therefore, if predicted demand growth requires substantial new resources and costs, the price of electricity might increase, which would in turn affect electricity demand. The demand forecasting system is iterated until the electricity prices and electricity demands were consistent. The demand forecasts also maintain consistency between the mix of resources in the power plant and the electricity pricing model, as well as the amount and timing of conservation program savings. Before the last power plan update, a significant new component was added to the demand forecasting system. As the Western electricity systems became more integrated through deregulated wholesale markets, and as we began to see capacity issues arise in the region, it became clear that we needed to understand the patterns of electricity demand over the seasons, months, and hours of the day. Therefore, the load shape forecasting system LSFS was developed. This model builds up the hourly shape of demand based on the underlying hourly shapes of electricity use by the different types of end-use equipment. It contains about the same detail as the demand forecasting system, but when multiplied by 8,760 hours per year. 1 year's forecast can contain 400 million values. DFS performance. The demand forecasting system has performed reasonably well for nearly 20 years. The forecasting models are started in 1981, so the ability to simulate actual demands can be checked for the historical period. The forecasts included in the 4th Northwest Conservation and Electric Power Plan was completed in September 1995. Therefore, several years of forecasts also can be compared to actual electricity sales. Historical and forecast performance of the demand forecasting system. Between 1981 and 1993, when actual values for input assumptions such as economic activity and energy prices are available, the average error of the model simulation was 0.4%. Between 1994 and 1999, when forecasted input assumptions were used, the average error was 1.0%. This error is reduced to 0.7% when the forecasts are adjusted for direct service industry policies starting in 1996 to make it consistent with actual sales data. Direct service industry sales are not forecast by the models but are done by assumption for each forecast scenario. Therefore, non-DSI forecasts are a better indication of model performance. Average forecast errors from 1994 through 1998 for non-DSI electricity sales and its major sectoral components. Errors are shown for public and investor-owned utilities separately. Uses of the demand forecasts. Quantifying the uncertainty of future supply requirements. The demand forecasting system is used to explore a range of possible future demand growth and the key factors that could lead to different electricity demand futures. The demand forecast uncertainty contributes one component of future uncertainties that are used to develop more robust, less risky power plans. Assist in assessing conservation savings potential and cost. The demand forecasts provide estimates of electricity using appliances and buildings. The potential savings from efficiency improvements will depend on the stocks of building. Changing prices will affect fuel choices and efficiency levels for these buildings and appliances, and how utilization of energy will respond to changing efficiency levels brought about by conservation programs. Provide a detailed understanding on electricity use and the causes of its change. Building up demand forecasts in sectoral and end-use detail provides the basis for understanding demand trends. It enables analysts to delve into the likely effects of economic trends, changing industry mix, demographic patterns, and changes in energy markets. It also provides a basis for predicting the importance of changes in energy-related technology, such as growing availability and lower prices for front-loading clothes washers or compact fluorescent light bulbs. A benchmark for monitoring regional electricity demand growth. Recently, the region and the council have had an increased need to track demand growth relative to available resources on a monthly basis. This has been necessary to help understand and manage the current electricity shortage and high prices. This use focuses more on near-term demand outlooks and the likely effects of weather on the monthly and hourly electricity needs. The current DFS and LSFS provide some information for this type of assessment, but are really more oriented to long-term forecast trends. A source of information for the region. Many entities in the region have relied on the Council's demand forecasts and the economic and fuel price assumptions that drive them as a source of credible information. This information is used in developing utility integrated resource plans, general education, and reporting about energy trends and corporate planning relative to energy requirements and markets. Although new generation development has largely become the province of non-utility generators responding to market signals, an independent assessment of possible future electricity demands apparently is still valuable. The Council responds to such requests for information almost daily from a wide variety of organizations and individuals. Alternatives for future demand forecasts. This part lays out some alternatives for demand forecasting for the fifth power plan and for the longer term. The alternatives for the power plan imply different schedules and budgets for the power division and produce different quality and detail in the forecasts. The longer term forecasting strategies have different regional data requirements, implications for council staff and funding, and require different degrees of regional effort. Alternative 1. Extend and modify existing forecasts without formal modeling. This alternative would perform a very simple update to the existing forecast range. Because the current forecast remains reasonably accurate, the changes would not be expected to be large. The demand growth rates could be modified to roughly account for any major changes in assumptions such as economic growth, fuel and electricity prices, etc., and develop new forecasts at the aggregate level needed to drive the resource planning models. End-use and load-shape details would be developed by using distributions from the old plan, possibly modified where we have evidence that the old forecasts may be in error. The advantage is that these forecasts could be developed relatively quickly. The focus of the plan would be on other issues and how they might be sensitive to different demand forecast scenarios. This may be the only realistic alternative that could result in revised forecasts within about a year. These forecasts would provide aggregate demand growth rates for the resource planning models and sectoral end-use detail of a comparable composition to the fourth power plan. The forecast results would not be supported by the large amount of detailed analysis that typically goes into a demand forecast. There would not be a detailed economic forecast to share with other regional agencies and businesses. Alternative 2. Squeeze another forecast out of the existing demand forecasting system. It might be possible to develop a full-scale forecast using the existing council demand forecasting system. Developing forecasts using the current demand forecasting system typically requires about 1.5 years. Detailed economic forecasts and other assumptions need to be developed. The models need to be extended to cover 20 years from the present, advisory committees need to be assembled, and models need to be recalibrated to recent demand characteristics and growth. This approach would provide the same level of detail and information available in the current council forecasts. There would remain the question, described above, of whether the more detailed end-use information is accurate. The revised economic inputs would provide information for many regional users as it has for the fourth power plan forecast. Alternative 3. Rebuild the current demand forecasting system. One alternative for future power plans would be to rebuild the current demand forecasting system. This would require two major efforts. First, the region would need to collect new data on current uses of electricity and other fuels at the sector and end-use level. Second, new forecasting models similar to the current council models would have to be developed or adapted to operate within the council's personal computer-based system. These models would need to be populated with region-specific information collected in the first step. Alternative 4. Develop a new, less detailed demand forecasting system. Another alternative for future demand forecasts would be to develop a new and less detailed forecasting model. Such a model would still be for individual sectors, address changing industrial compositions, and capture the effects of electricity and fuel prices, but would not provide the detailed end-use efficiency information that has characterized past forecasts. This approach would weaken the consistency between conservation analysis and the demand forecasts. The models could be oriented more to the mid-term than the very long term. Such an approach would serve to provide inputs to resource planning models but would not inform conservation analysis in the same way as past council analysis. End-use information would have to be allocated based on old demand model results or other information. The forecasts of demand would not automatically adjust for efficiency changes in equipment and building shells. There would be no estimate of behavioral changes in consumption as a result of efficiency changes. We could not run frozen efficiency, price and sales forecasts as we do with the current forecasting system. Forecast ranges could be developed based on some important aggregate input assumptions, but it would be more difficult to explore uncertainties in the end-use details of the forecast. Simulation of queuing problems. A queuing system is described by its calling population, the nature of the arrivals, the service mechanism, the system capacity, and the queuing discipline. In the single-channel queue, the calling population is infinite. That is, if a unit leaves the calling population and joins the waiting line or enters service, there is no change in the arrival rate of other units that may need service. Arrivals for service occur one at a time in a random fashion. Once they join the waiting line, they are eventually served. In addition, service times are of some random length according to a probability distribution which does not change over time. The system capacity has no limit, meaning that any number of units can wait in line. Finally, units are served in the order of their arrival. Arrivals and services are defined by the distribution of the time between arrivals and the distribution of service times, respectively. For any simple, single or multi-channel queue, the overall effective arrival rate must be less than the total service rate, or the waiting line will grow without bound. When queues grow without bound, they are termed explosive or unstable. More complex situations may occur. For example, arrival rates that are greater than service rates for short periods of time, or networks of queues with routing. Simulation of inventory systems. An important class of simulation problems involves inventory systems. This inventory system has a periodic review of length n, at which time the inventory level is checked. An order is made to bring the inventory up to the level m. At the end of the first review period, an order quantity Q1 is placed. In this inventory system, the lead time, that is the length of time between the placement and receipt of an order, is 0. Since demands are not usually known with certainty, the order quantities are probabilistic. Demand is shown as being uniform over the time period in figure 9.9. In actuality, demands are not usually uniform and they do fluctuate over time. One possibility is that demands all occur at the beginning of a cycle. Another is that the lead time is random of some positive length. Notice that in the second cycle, the amount in inventory drops below 0, indicating a shortage. These units are back-ordered. When the order arrives, the demand for the back-ordered items is satisfied first. To avoid shortages, a buffer or safety stock would need to be carried. Carrying stock in inventory has an associated cost attributed to the interest paid on the funds borrowed to buy the items. This also could be considered as the loss from not having the funds available for other investment purposes. Other costs can be placed in the carrying or holding cost column: renting of storage space, hiring guards, and so on. An alternative to carrying high inventory is to make more frequent reviews and consequently more frequent purchases or replenishments. This has an associated cost, the ordering cost. Also, there is a cost in being short. Customers may get angry with the subsequent loss of goodwill. Larger inventories decrease the possibilities of shortages. These costs must be traded off in order to minimize the total cost of an inventory system. The total cost or total profit of an inventory system is the measure of performance. This can be affected by the policy alternatives. In an inventory system, the events that may occur are the demand for items in the inventory, the review of the inventory position, and the receipt of an order at the end of each review period. When the lead time is 0, the last two events occur simultaneously. Summary. Now in the end, let us summarize what we have learnt in this lecture. Simulation is especially useful if changes in an existing system are to be made and the effects of the changes should be tested prior to implementation. Simulation is often the only means to approach complex systems analysis. Monte Carlo simulation is a technique used to determine the probabilistic distribution of an outcome that relies on all probable scenarios. Monte Carlo simulation is done using risk analysis software. A queuing system is described by its calling population, the nature of the arrivals, the service mechanism, the system capacity, and the queuing discipline. The demand forecasting system is still capable of simulating and forecasting electricity demand at these fairly aggregate levels.